Okay, all right. So, good morning, everyone. So, today's the first lecture is going to be trying to build some of the background needed for what we are going to do in model approximation. There are a lot of details in what I am going to talk about. I will try to convey the high level idea, and for some of the details you will have to look at the notes. The details are basically simple algebra, but it gets a bit tedious to derive. So, let us see how we are doing, and we will come to that. There are sort of three important topics that I want to cover today. The first is just that all of our analysis is going to be based on a basic technique, and writing the dynamic program in full every time becomes a bit tedious. So, I am going to introduce a shorthand notation which will simplify describing what we are doing. Okay. So, let us just start by reviewing what we had done last class with a little bit more notation. So, I will use the notation. So, for the next 4 lectures or so, we will be focusing on full state observation in MDPs. So, I will use the notation of saying that I have a model M denoted by state space S, action space A, transition dynamics P, per step cost C, and a horizon T. This is sort of the shorthand notation that I am going to be using, and in this notation P is really a collection of transition matrices over time, C is a collection of per step costs over time, and we are assuming this is of the form of P of Pt of S prime given S and A, and this is of the form sum cost of current state and action. Okay. Now, in last class we defined 2 dynamic programs. One was an optimality dynamic program, and this worked by starting from a V star t plus 1 which was 0 and writing we define the q star t at S and A to be equal to C t of S A plus summation over S prime P t S prime given S A and V star t S prime, and then computing V star t of S to be minimization over actions q star t of S A and defining pi star t of S to be one of the argmins of this step. Okay. And we had a policy evaluation dynamic program which was similar. In the interest of sort of time, I am going to focus on optimality DP most of this lecture, but everything that we do would be applicable for policy evaluation dynamic program. The point to keep in mind is in the policy evaluation dynamic program, what are the things which change? I am starting with V pi t plus 1 which is 0, and at this step I am going to be replacing star by pi. Here I am going to be replacing star by pi, and in this step instead of doing minimization we are simply evaluating the q function at a particular time, right. So, the basic structure remains the same, except that I am instead of optimization I am doing evaluation. Yes, thank you. This should have been t plus. Okay. So, in the MDP literature, this is written in a short form using what are called Bellman operators. Typically, this is done for infinite horizon problems. I'm not going to be talking about infinite horizon problems in this course, but this is still a nice shorthand notation. I'll describe what this notation is, but we'll not use this notation in the course because I think this is a bit too coarse for the way I want to look at the problem. And after that, I'm going to be defining an alternate notation, which is not used in the literature, but I think that makes the analysis much, much more transparent. So, just we are going to use script V. This did not turn out well. I don't know how do I write that. So, let us say this means script V, and this is the space of value functions. So, these are all functions which are, this is the set of V's such that V maps S to reals. So, when I am in a finite dimensional space, this space will be effectively equivalent to R to the S. Any function from a finite set of variables to something can be thought of as a vector in a Euclidean space. And I am going to use script Q to denote the space of Q functions. Now, the Bellman operator, the way it is defined, is an operator. It is an operator at time t. There is an optimality Bellman operator and there is a policy evaluation Bellman operator. The optimality Bellman operator is a function from this space of value functions to the space of value functions. So, it takes a value function and gives me a value function, and it is defined by B star of t for any value function V. So, this is an operator whose input is a function, its output is a function, and I am going to now evaluate that output at a particular point. This is minimization over A okay. So, basically what I have done is I have taken this part, V star t is minimization of this guy, and I am saying I am going to think of this as an operator which takes an input which is this value function and gives me an output which is this value function. Okay. Sorry, sorry about that. This is just V of that. Okay. So, with this notation, basically I can write my DP compactly as V star t plus 1 is 0, and then V star t is the Bellman optimality operator at t applied to the optimal value function at t plus 1. Okay. So, rather than writing these complicated operations, I can just write this in a compact form. Policy evaluation Bellman functions are defined differently, are defined similarly with this instead of minimization replaced by policy evaluation. But since I am not going to be using these operators anyway, I will not go into the detail of policy evaluation operator. Okay. Now, the reason why people like to use that in MDP theory is that if I am interested in finding some property, so you see, if you see from last time, most of our proofs are working in backward induction. We show that the value function has some property, and if I can show this operator preserves that property, then I will have that the next value function has that property. Okay. I feel that this is trying to do too much in one single step. So, I am going to break down this operator into two operators. so that I have a decomposition which is similar to the way I have been writing dynamic program in 2 steps. Okay. So, and sort of this is an non-standard notation, no one uses it, but I think it simplifies things. So, I am going to define 2 operators. I will call an environment or model operator. This I will denote by ET. This is an operator which takes a value function and gives me a Q function. So, it is an operator from the space of value functions to the space of to the space of Q functions, which means if I take any value function and I apply this operator, I will get a function which I can evaluate at some S and A, and this is the cost at S and A plus summation over S prime Pt of S prime given S A V of S prime. Okay. And now I am going to define 2 other operators which I am going to call action evaluation operators. And I am going to use let's see what's the best way of writing this, script T star, which is an operator which takes a Q function and gives me a value function, and an operator T pi which takes a Q function and gives me a value function. Okay. The way I am going to define this is that T star applied at some Q function little q evaluated at S is arg min over actions of Q of S A, and T pi evaluated at some Q function of S is Q of S and pi of S. Yes. And I will also define another operator which I will call the greedy operator. This is an operator which takes a Q function and gives me a policy. Okay. I will generally define it as a correspondence to the set of policies. So, that is, it can give me a set of policies, and G of Q is really the set of arg min over A of Q of S A. Okay. So, I am just defining some notation which will make it easier for me to write down my DP. Okay. So, now what I can do is I can go and I can say that my optimality DP is given by V star T plus 1 is 0, and then I am doing Q star T plus 1 is the environment operator applied on V star T plus 1, sorry, Q star T, and then V star T is the optimality action evaluation of Q star T, and the optimal policy is anything in the greedy policy corresponding to Q star T. Okay. So, this is just a short form notation rather than having to write all these things in detail. And I will write now the policy evaluation dp to be v pi t plus 1 equals to 0, q pi t is the environment operator applied on v pi t plus 1, and v pi t is the policy evaluation operator of pi t applied on q pi t. Okay. So, I have a short form for writing my dynamic programs. This is the notation that I will be using in the rest of the course, rather than having to write down the dp in detail like this. And one small remark, that this notation is also applicable when my state spaces are continuous. I was writing this as summation. When this is continuous, I will have to do an integral with respect to some conditional measure and so on. That is kind of implicitly captured in this notation. If state spaces are continuous, that is what I mean. Okay. Occasionally, I will use two other operators. I will use an operator script pt, which takes a value function and gives me something in the space of q functions, and ptv evaluated at SA is simply summation over S prime pt of S prime given SA v of S prime. Okay. This is the second half of this guy. So, in some cases, I am just interested in what is happening with without looking at the cost function. The nice thing is pt is an linear operator. This guy et is an affine operator. Now, the reason I prefer this notation over Bellman operators is because now I have a very clean separation on in the dynamic program, what is the part which depends on the underlying model. It is how I go from a value function to a q function. Then I have a second step, which is how do I go from a q function to a value function. That depends on whether I am doing optimality or policy evaluation. That step does not depend on the model. That step is completely model free. Okay. So, what we are going to do later on is when we do look at approximation properties or other properties of the value function, I can talk about a property and say what happens to that property with respect to the environment operator, and what happens to that property with respect to the policy to the action evaluation operator. Okay. Any questions on this notation? All right. So, let me now give a motivation for why am I interested in model approximation in a concrete setting. So, in the notes I have an example of a continuous state MDP. For the purpose now, I am not going to define the precise model, but just abstractly ask the following question. Suppose I have a model in which my state space is some continuous interval. Let me say some bounded interval from minus b to b, and my action space is discrete, just for simplicity. Okay. So, the dynamics that I have in the notes is something of ft plus 1 is ft plus WT truncated to minus B to B if I take action equals to 0 and it is equal to WT if action equals to 1. Okay. So, I have some physical system which say evolves as follows. And what would be given in this case is, suppose I am given a distribution on this noise and I am given a per step cost which let us say is S square plus lambda A. Okay. I do not really want to discuss what is the motivation for this example because that is not important for this model. I will just assume it has a support which is within minus B to B, but if it is not, then you will truncate it. Okay. So, now how do I solve this problem? Okay. How would you do that naively? What is the simplest way of solving this dynamic program? Right. What I will have to do is, at some stage I have to solve this step Ct of Sa plus expectation of Vt plus 1 of the dynamics given Sa and W, where this expectation is with respect to my noise. Right. But this is a continuous random variable. I have to solve this for all values of state, I have to solve this for S and A, but this is also continuous. So, I have two difficulties. How do I take the expectation when I am taking the expectation with respect to a continuous random variable? This is complicated, but this is easy to handle. There are various techniques through which I can take an approximate expectation of a continuous random variable. In the simplest setting, if I know the distribution, maybe I can use some algebra to figure out what this is. Worst case, I will do something like Monte Carlo to compute this expectation. So, I will not worry about the expectation. But what do I do with the state space? My state is the set of real numbers between minus B to B. How do I compute a function over that space? Okay. What is the simplest thing I could do? Okay, discretize the state space. Okay. How will I discretize the model? What is the obvious way to discretize the model? I am going to say this is my interval minus B to B. I will partition it into bins. Right. Let us say I do something like this. Right. I do make a grid on this space, and I am going to say for every grid cell, I will call it script Cj. This is the, so this is going to be 1 to n. I make n grid cells here. For any grid cell this, in discretization, the simplest way is I will pick a representative element. Okay. I will call this representative element S hat j. Okay. And now there are discrete number of points. I will try to construct a estimated p hat of S hat j conditioned on S hat I and A. I need to construct a approximate dynamics. Okay. There are various ways to do this. The dumbest way to construct a approximate dynamic is to say I will call this to be equal to the probability of going to cell Cj starting on point S hat I and A. I know I have a dynamics on the underlying space. So, if I am thinking of the probability of going from the point Fi to point F this, I will say what is the probability that from this point I can go to this entire interval, and I will assign that mass to be equal to this thing. Okay. This is one way of doing it. This is not the most elegant way of doing it, but this will work. And yeah. Yes, it is dependent on the choice of the representative element. I am just assuming I am doing uniform grading and I am taking the center of the bin as my representative element. Okay. In a more sophisticated manner, you are going to put a weight on your point, and you'll integrate the flow according to that weight. It doesn't really change anything. It will just make my representation a bit more complicated. Okay? And I can compute a function c hat, and I can say c hat of s hat and a. In the simplest way, I can just say this is c of s and a. Okay? Yeah. This is, I'm just saying this is a transition kernel, so this will satisfy, I'm creating an completely made up Markov chain with a given dynamics. Right, so I'm just specifying the transition kernel of the Markov chain.
The way I'm looking at it, you are sort of grouping states, right? And then you are looking at transitions on the group states. At least that's how I'm looking at it. Then the transition on the group states need to satisfy some property so that the resulting thing can be called.
Yes, but that's why I'm not doing that. I'm not doing, so I'm doing state aggregation in a very, very different way, and all I'm saying is, so you are right, I could have said this all thing is going to be one state, this is one state. If I want to follow that and ensure that I have the Markov property, I'll have to assume there is a conditional measure on this set given that I'm on s hat I, there is this conditional measure on c hat I, and I'll average the flow over all of these things here to what is I'm going there. Okay? That would also, so if I take a trajectory of the Markov chain, of the continuous state Markov chain, and I bin the trajectory, that is not Markovian. Okay? What I am saying is I'm not going to do that. I'll just pretend I have a Markovian model. Okay? And this by construction is a Markov chain. Now, this Markov chain is not equivalent to the chain obtained by binning the continuous state Markov chain, but the intuition is that if I have appropriate smoothness, this is going to be roughly the right thing to do. Okay? So, that is why I am saying this is not necessarily the most accurate representation that I can get by discretization. This is the simplest way to do discretization. Right? Now, once I do discretization, then what? I'm going to solve the dynamic program on this discretized model. Okay? So, what that gives me is, going back to this guy, for simplicity, let me just say I had done 1, 2, 3, 4, 5 bins, okay, just so that drawing things are easy. In this model, I have my representative elements s hat 1, s hat 2, s hat 3, s hat 4. Okay, I ended up with 6. So, never mind, s hat 6. Okay, I have 6 elements. I have constructed a transition matrix on 6 elements. I have constructed a cost on 6 elements. So, when I solve my dynamic program, at every time I'll get a value function on these 6 elements. So, let's say I get something which looks like this. Okay. I can now think of, when we do discretization, so think of how would you run a simulation if this was your discretized thing and you are plotting the value function. You would not plot it using a stem plot. Okay? In an ideal case, I would present it in the same thing as we think of Riemann integral or something. I'm going to draw these piecewise constant values in each one of these bins. And I'm going to claim this is my approximation of the true value function. Okay? There will be a similar approximation for the policy. For the time being, I'll not worry about the policy. Okay? So, one question is this a good approximation? Okay? So, clearly I know from continuity intuition that as I keep on increasing the number of bin points that I have, this approximation will become closer and closer to the true value function. Okay. Let us say the true value function was something like this. Okay. And I know with this discretization, I have obtained some approximation of this true value function. When I get more and more bins, I will get tighter and tighter approximation. And depending on what application I am doing, I will be happy when I have an approximation within, which is within some alpha error of the true value function. So, in an ideal world, I want to say pick the number of bins which are high enough, so that my approximation is within some alpha bound of the true value function. How do I provide such a guarantee? If I cannot compute my original value function. You see, if I could compute this original value function, I don't need to do approximation, right? If I had the ability to, let's say in this case it's trivial, I could say I'm going to do discretization at, I don't know, 10 to the minus 3. For all practical purposes, that's a continuous thing, so things are going to work. But if I were in 10 dimension, I cannot discretize my state space to 10 to the minus 3. I'll have too many points there. So, I have to do something more fancy in terms of my approximation. But the question really is, I cannot get a very accurate representation of the true value function. I want to construct an approximate model which gives me an approximation and a guarantee that my approximation is close to the true model. Okay. We will focus on this question in the next class, but the key point that I want to emphasize today is, this is something which someone had raised in the class yesterday, is the quality of approximation is going to depend on the properties of the true value function or the properties of the approximate value function. Okay. I need to know something about how smooth this value function is in order to say how good my approximation is going to be. Now, in order to do that, at the core of it is the following question. Okay. Suppose this is the problem in the simplistic setting. Suppose I have some state space S and I have a value function from F to R, and I have two measures, mu and I have nu in my notes. So, hopefully, you could be able to differentiate between my nu and a v. These are two measures on S. Okay. So, in terms of what's going to happen in my original problem, I have it's a bit more complicated there, but I can think of, let's say I have some dynamics on the starting from state S hat, which was saying I have some probability distribution of going over this space, right. That distribution conditioned on S hat and an action would be some curve like that. And what I said was, I am going to pretend that's a straight line which is equal to the area under that curve. That's the approximation that I did here. Okay. So, the question is, I had a true dynamics, I approximated it in some way, and what I would like to do is that when I do this expectation with respect to the true dynamics versus if I do the expectation with respect to the approximate dynamics, how much do they differ? That's the core question. If I can understand this, I can build on that to say what's going to happen to my approximation error, right. So, this question I can state as, what happens when I look at the average of v with respect to mu minus the average of v with respect to the measure nu. Okay. And apologies for my nu and v, but hopefully this would be clear what I mean by what. Okay. How do I get this bound? Okay. So, I am going to work through this to develop intuition on how can we get bounds on difference of expected values, and point out to sort of a general theory from general branch of probability theory, which gives us a easy way to define these distances. Okay. What I really, the type of bound that I want to get is that this bound, this is going to be upper bounded by some type of distance between the measure mu and nu and some property of the value functions. Okay. So, the nature of the bound that I want is that this should be less than equal to some distance between mu and nu and some property of the value function. Okay. We have to figure out what are the types of distances which make sense, what is the type of property that makes sense. Okay. So, let me do this from like very, very simple way. I have something like this. Let me do the following. I am going to say, so this is take 1. This is not how we do things, but I want to develop intuition. So, let me do, I am giving a solution which is the simplest, not the most accurate. What I am interested in is summation of, I am going to write this as mu of s minus nu of s multiplied by v of s, absolute value summed over s. This is the difference of expectations. Okay. So, I can say this is going to be less than or equal to summation over s, absolute value of mu of s minus nu of s times absolute value of v of s. This is just triangle inequality. Okay. I can say this is going to be less than equal to summation of s mu of s minus nu of s into sup norm of v, okay, where this notation is the in general supremum over all s in my state space v of s, right. So, this is the maximum value that the value function will have. I am going to be using this quite a lot, and this is the only norm that I will be using. So, most of the time I will not write infinity here. I will just say this is the sup norm without writing infinity, just to simplify notation. Okay. So, I get something like this. Now, this quantity does not depend on s. So, it comes out of the summation, and I am left with essentially what is the L1 norm between mu and nu multiplied by the inf norm, sup norm of v. Okay. You may realize this as a special case of Holder's inequality also. Okay. So, this is one bound I can get which has this characteristic. I got some notion of distance between mu and nu, the L1 distance between them, and some property of my value function, which is the sup norm of the value function. Yeah. Yeah. I would rephrase that as, so this is one way of doing that. Okay. There are other ways of doing that which will give you different bounds. Okay. So, this is one way in which I want to separate out the impact of the model, and you will see later on when we derive bounds, this allows me to get very, very nice bounds on the approximation error. Okay. I am not claiming this is the only way to do it, but this does separate out, some of it will become clear when we look at the next lecture on how do we get approximation bounds on that. Okay. So, it's more of a philosophical question than anything technical at this stage. Okay. So, this is clear to everyone. This is, I can get bounds of this type. Okay. But this is a bad bound. Why is this a bad bound? Let us go back to this. Okay. Suppose I add a constant to my value function. I have a value function, I am taking its expectation with respect to two measures. I add some constant. That is going to increase the expected value of with respect to the first measure with a constant. It is going to increase this expected value with a constant. So, the change in the difference of expected value is nothing. This difference is indifferent to adding a constant to my value function. This bound is not. Okay. So, clearly this is a loose upper bound. This is all the steps are correct, but this is not the tightest way in which I could have done the upper bound. Okay. How can I fix that? Yes. So, what I can do is I can ensure that this function is such that its maximum is equal to minimum. This is a centered function. Okay. That's, I can add any constant to make sure that this function becomes centered, and in that case what I'll have is not the sup norm of the function. So, what I'm going to be doing is, suppose I had a function which was like this. I'm going to say I'm going to move the function so that the 0 becomes this dashed line, and now I look at the sup norm with respect to this dashed line. Okay. That, an equivalent way of representing that is I can say this quantity is known as the span of the function. This is the maximum minus the minimum of the function. So, the best bound that I can get here, with a little bit effort, I can show that I can actually get a tighter bound, which is going to be mu minus nu L1 norm and half of the span semi-norm of V, okay, where span is, as I defined here, span of V is going to be the max over S of V of S minus min over S of V of S. This is max minus min if I am in compact state spaces. In general, this will be sup minus inf. Okay. So, I can get a tighter bound of this type. Okay. This is used quite a lot in the literature. This object is called the total variation distance between two distributions. Okay. In some of the literature, total variation is defined as something which is 1/2 of this. I am going to be following the convention that total variation is equal to the L1 distance between measures. Okay. So, if you are reading some other source, there may be a difference in constant here, and then you will get span here rather than half of span, but it is the same thing. All right. So, this is one thing that I can use to say that the distance between expectations with respect to two measures is equal to the total variation distance minus the span norm. Okay. Now, there is a interesting thing in probability theory, which are, I can define distance between distributions as a solution to a dual program. Okay. So, this is what is typically known as a primal definition of distance between measures, that I am defining this directly in terms of properties of my distribution. I could have given an alternate definition. I could have said that the total variation distance between mu and nu is equal to the supremum value of the mu of S V of S minus nu of S V of S, such that half span of V is less than equal to 1. So, I define a set of functions, which is the functions whose span norm is less than equal to 2, or half of their span norm is less than equal to 1, and I say what is the maximum distance that I can get between these two distributions. I will define that as the total variation. Okay. This is equivalent to saying that all the inequalities in this relationship I can make tight. There is some choice of measures for which the triangle inequality is tight. There is some choice of measures for which all of these terms are equal to their sup norm or the span norm, and then this guy is actually an equality. Okay. I will not go into the proof of this. Let us just believe me for this, that I can define things in terms of a dual distance. Okay. So, the I will come back to this later on. Okay. So, this is one distance, but total variation is not a good distance. Let me try to give some motivation on why total variation is not a good distance. Suppose I have some distribution, let us say I will draw a PMF. This and this. Okay. This is my true distribution, and I construct an approximation. This is mu. This is my first approximation nu 1, which takes some mass from this point. So, it reduces this mass and puts this mass on the second point. Okay. And I take another distribution nu 2, which takes the same mass, but puts it in this guy. Okay. Now, the L1 distance between mu and nu 1 is same as the L1 distance between mu and nu 2. Total variation does not care whether I move this mass to this point or to this point. Okay. But if I am right in a physical world where I had ordered these things in respect to some natural distance on the space, then I care about whether I went to a nearby space or did I went to a faraway space. Okay. So, if I have a good notion of distance in a metric space, that distance should be defined in terms of the metric. Okay. There are various types of distances I can define in terms of the metric. One such distance is the Wasserstein distance. Wasserstein distance has a primal definition in terms of optimal transport. There is a very rich history of this field. It would probably take 2 courses just to cover everything which is there in Wasserstein distance. So, I am going to do a cop out and give a definition of the Wasserstein distance, which is mathematically correct, but I am going to give the dual definition of the Wasserstein distance, and we can, for our purposes, that is going to suffice. This is not a complete description. I am sort of hiding certain things. So, sort of you will have to do some background reading on that, but the idea should be clear on why Wasserstein distance works as a good distance for what I want to do. So, in the Wasserstein theory, there is a primal definition of the distance, and there is a dual definition which is in terms of Lipschitz constants of functions. So, first let me do define what do I mean by Lipschitz constant of functions, and then we will come back to this. Okay. How many of you have seen what a Lipschitz constant is? Okay. So, suppose I have a space which is a metric space, and I will use D of S to denote the metric. Okay. So, suppose I have a metric space and I have a function V from the space to reals. I can do this over general sets also, let us say over reals. Okay. So, effectively I am from one metric space to another metric space, where over reals it is the Euclidean metric or the absolute value, which is the natural metric on this space. So, I am going to define the Lipschitz constant of a function V is equal to supremum over 2 points S and S prime in my state space. This is going to be a ratio. The numerator is V of S minus V of S prime, and the denominator is the distance between S and S prime. Okay. So, roughly what the Lipschitz constant says is that if I take a function, I am going to look at the derivative of the function at every point, and I am going to say what is the maximum absolute value of the derivative. This means that if I get something for the Lipschitz function, then at all points my function is going to be within a slope which is bounded by plus minus of the Lipschitz constant of the function. Okay. So, if I imagine Lipschitz constant is according to some slope, and I draw this kind of a cross thing and move it across the function, at every point my function would be in this part around that. So my slope never goes beyond a maximum and a minimum slope. That maximum and minimum slope is the Lipschitz constant of the function. Okay. The way it is defined, this is something which will be between 0, but it can take a value infinity. We say V is Lipschitz if the Lipschitz constant of V is strictly less than infinity. Okay. So I'm going to rule out cases where I have a function which can have infinite deviation. An example of a function which will have infinite Lipschitz constant is something like square root of s. Right? Square root of s goes something like this, and the slope is going to infinity as I get closer and closer to the origin. So the Lipschitz constant is infinity. Okay. Now, the relationship between Lipschitz constant and Wasserstein distance is that there is a result which is known as Kantorowicz Rubinstein duality, which says that the primal definition of Wasserstein distance is equivalent to the following. Wasserstein distance between measures mu and nu is equal to the supremum of the absolute value. I'll write it for discrete spaces. The same thing goes for continuous spaces. This is a simple result in sort of duality. If you've seen dual results in linear programming, this is sort of the same derivation as a no duality gap in linear programming. That if we look at there is a primal optimization problem which gives the Wasserstein distance. If I look at the dual version of that, it gives me the same distance. So there is no duality gap. But I'm going to just take this as the definition of Wasserstein distance. This looks like a horrendous definition because I cannot compute it, but there are ways to compute it. This can be computed by solving a linear program. So when I'm in discrete spaces, I can compute this. In continuous spaces, there are different ways to approximate Wasserstein distance. We will not go there. Okay? But the good thing with both this definition and this definition is that such dual definitions make it very, very easy for me to get a bound of the type that I had written here. Okay? Let me show that in terms of Wasserstein distance. So the basic idea is, suppose I'm interested in looking at the expected value with respect to mu of s nu of s minus nu s vs. Now, if the function v had a Lipschitz constant which was less than 1, I know this quantity will be less than equal to the Wasserstein distance between the measures. Okay? Because that was my definition of the Wasserstein distance. I'll supremize over all functions whose Lipschitz constant is less than 1. So if its Lipschitz constant was less than 1, that's just the definition of sup. What do I do if I have a function whose Lipschitz constant is not less than 1? If I just divide it by its Lipschitz constant, the resulting function will have a Lipschitz constant less than 1. Okay? So I can write this quantity as the Lipschitz constant of the value function multiplied by summation of mu of s, nu of s divided by Lipschitz constant of v minus summation of nu of s, v of s divided by Lipschitz constant of v. And now this function is a function whose Lipschitz constant is less than b. Therefore, by definition of Wasserstein distance, this should be less than equal to the Wasserstein distance between mu and nu and the Lipschitz constant of the function v. Okay. I get the same type of result that I had gotten for total variation. Okay. And this is a general principle. What I can do is, so you see, all that I required here was I defined distance between probability spaces in terms of maximize the difference of expected value over a class of functions which belong to some function space, right? And when I have to compute the difference of expectations, I just say, can I scale that function in such a way such that the scaled function belongs to the function space, and then I'll get this result. Okay. So in probability theory, there is a general name for distances of these type. This is known as integral probability measure. Abbreviated to IPM. This measure is defined with respect to some function class f. This is some function class. This has to satisfy certain properties. This has to be convex. This has to be balanced. Balanced just means that if f belongs to script f, that implies negative f should also belong to script f. Okay. So it should look like a ball, basically, right? It is something which is convex, and it has this property that things should belong in if I flip them. There's some other properties which are not important, so I'll not describe this in detail. I have links in my notes to a detailed description of IPM, and you can look at that. But the point is, given this set of functions, the IPM distance with respect to this class of functions between two measures mu and nu is defined as supremum over all functions which belong to that function class. The expectation with respect to mu, I wrote it as f, so let me write it as f, minus summation with respect to nu and now total variation is an IPM where the class of functions is functions whose half of the span norm is less than 1. Wasserstein distance is an IPM where the class of functions is the functions whose Lipschitz constant is less than equal to 1. Okay? Yeah. No, you'll have to look at the primal definition for how Wasserstein distance addresses that. Sorry? Yeah, so that's kind of the thing, right? But it's hard to directly see that how the Lipschitz constant is going to impact that, because I'm just, so you see, the primal definition does not depend on having a function and I'm supremizing or infimizing over the function. It's just properties of this thing. So it will be a longer discussion to explain why the primal definition does that. We can talk after the class to explain that. I sort of, in the interest of time, I don't really want to go into the details of that. Okay. Because for general spaces, this is an integral. Okay, so I'm just writing it for discrete state spaces, but this will be integral with respect to the measure of the function and so on. All right. Now, what was the key property that allowed us to get our bounds here? It was the fact that if I take a function which does not belong to my function space, I can scale it in such a way so that it belongs to my function space. Okay. This is a general tool used in analysis. This is known as the Minkowski functional. In some of the physics literature, this is also called a gauge. But it's a simple definition, so don't worry if you haven't seen this before. I'll say the Minkowski functional with respect to a function class f of a function little f is equal to infimum over all real numbers greater than 0, such that f divided by that r belongs to the function class. Okay. And the intuition that I want you to have is that for the definition of this IPM, my function class is some kind of a ball. Okay. And if I take a function outside this ball, all I'm saying is that maybe I can scale this function, and what's the smallest amount by which I have to scale it so that it comes inside the ball. Okay. If this is truly a ball, the amount by which I have to scale it is equal to whatever distance I was using to describe this ball. Right. So in the case of total variation, the Minkowski functional should be half span of the function. In case of Wasserstein, this should be the Lipschitz constant. Okay. The only reason where, only case where this thing breaks down is if this ball was in, let's say, 2 dimension and my function was in the 3rd dimension. Then no matter how much I scale it down by, the only way to come back to this ball is to make this thing infinity. Right? And in that case, this thing will be taken to be assumed. So I'll take this to be equal to, sorry, the Minkowski functional would be, yeah, I have to scale it down by infinity to bring it down here. Okay. Or equivalently, there is no value of r which brings me to this function, and therefore the infimum of an empty set will be infinity, right? For whichever way you want to interpret it. But this definition and this definition immediately give me the following. For any function f, summation of mu of s into f of s minus nu of s into f of s. So difference of expected values is going to be equal to the Minkowski functional of the function times the IPM distance between the measures. So I get inequality of the type that I wanted. That I have that the difference in expected values is equal to a property of the function and some kind of distance between the measures. I've been writing all of these things in terms of discrete spaces. Everything goes through with continuous spaces. You'll have to put appropriate measurability assumptions so that everything holds. In general spaces, I'll also have to worry about that this expectations are well defined. So I'll have to work with class of functions so that I don't get infinity minus infinity and so on. So when you read the technical description of these things, it seems a bit heavy because people define in terms of all these fancy spaces and so on. But it's a very, very simple idea. Okay. I'm going to focus only on total variation and Wasserstein for the purpose of the bounds that I derive. But this allows us to give a whole family of bounds by just changing the type of IPM that I have. And there are like 5 or 10 different variations of IPMs which are considered in the literature. Depending on your application, a different IPM may be a better choice to talk about the approximation error. Okay. Any questions on this? Okay. So these were 2 things. One is the notation that we are using for dynamic programming. Second is this idea of IPM and the fact that if I have this dual definition of distance between measures, I get a bound of this type. I have about 20 minutes. I'm going to talk about try to give some intuition about the getting some bounds on properties of value functions. Yes. Mhm.
So how is this bound? Okay, are these bounds tighter or are these bounds richer in the sense that maybe we can cover different characteristics of distributions and functions? What is the advantage?
So, the one advantage is, so there is a lot of results in the literature where someone gets one bound in terms of total variation, then you repeat the same analysis and get a bound for Wasserstein, repeat the same thing and get this for MMD distance. It's the same analysis, right? So, it helps separate out basically just changing the IPM doesn't change the nature of the bound. So, that's one thing. The other thing is this question about like swoop norm versus half span norm. So, in the IPM literature, there is this notion of, so this is called the generator of the distance between them, and there is this notion of the maximal generator of a metric. And essentially, you will not end up with things like I'm using a swoop norm, which is a bad upper bound rather than half span norm, if you had started with a maximal generator of the IPM rather than any generator of the IPM. So, there is part of that theory which in principle helps tighten the bound, but for specific metrics people already know which the tighter upper bound is, but it I think gives a cleaner way to look in terms of that. I mean, just at a high level, right? So, this is one type of bound. The other type of bound I can get is, rather than getting a bound on the difference of expected values, I can try to get a bound in terms of ratio of expected values. And then you'll start getting things like KL divergence and so on, because that's the natural metric if I'm looking at ratio of expected values. In that if I want bounds which are additive form, this I think is the only way I can get these bounds.
Related question. Sometimes capturing these distances are important, but also you want to optimize against these distances, right? So do you think these allow for that as well? Like the KL divergence in some sense is popular because of that reason.
So we have a lot of experimental results where we say this is relatively easy to incorporate in like a learning algorithm in terms of approximating these bounds. So one point is KL divergence. I can get a bound in terms of KL divergence from total variation using Pinsker's inequality. So it's a very, very crude upper bound on total variation, because total variation is bounded by 2, while KL divergence can go to infinity. But if I want KL divergence, I can get KL divergence from that. Sort of, there are other things which I probably can discuss offline, and there are certain instances even for things like TRPO and so on, we believe IPM is a better way to look at it than generally KL divergence, where it is just use an upper bound on total variation in that analysis, and using general IPMs gives more general theory, and also some experiments we have seems to suggest that actually works much, much better. Okay. Now, what I want to focus on, yeah. No, that's the primal definition. So here I'm just supremizing with respect to class of all functions whose Lipschitz constant is less than 1. Okay? The primal definition is I have the distance function and I look at all the couplings with the same marginals which minimize that distance. So that's why I'm saying, right, it's similar to, I have an infimization problem, the dual will be a supremization problem, the constraint becomes the constraint on the Lipschitz constant there. Okay. So I have now two bounds which I want to work with, that the difference of expected values is less than equal to either the total variation distance between mu and nu and the span of v, or this is less than equal to the Wasserstein distance between mu and nu and the Lipschitz constant of v. So what we'll be doing in next lecture is sort of getting approximation bounds in terms of span norm of the value function and span norm of, or the Lipschitz constant of the value function. So, I just want to provide some intuition on the fact that based on the properties of my model. So, based on properties of C and P, we can get bounds on the span of V star t and the Lipschitz constant of V star t. Yeah. You'll see that that comes out as an intermediate step when we are computing V star. They go hand in hand. Okay. So, trying to think which is the best way to cover this. So, last time when I asked, most of you have taken a course in Markov chains. Did you look at ergodicity in Markov chains? Has everyone seen ergodicity coefficient in Markov chains? Can you raise your hand if you have? Okay. So, this is a crash course in ergodicity. Let's see. So, I am going to be interested in saying, so if I look at the update equation on what is happening with my dynamic programming equations, so let's think of a Markov chain with transition matrix P, and I ask the following. Can I say what happens to the span of PV in terms of the span of V? Is there some relationship between the span of a function? I pass that function through the Markov chain. So, I do the averaging of that function by multiplying with respect to the transition probabilities of the Markov chain. Can I say something on what happens? Okay. It will be less than equal to, but I want something better than less than equal to. So, less than equal to is a good intuition, because what the Markov chain is doing is it's taking stuff and it's mixing it together. Okay. So, if I mix things together, the maximum variation that I can get reduces. So, I know this has to be less than equal to the span of this. What ends up happening in a lot of Markov chains is that it's actually strictly less than equal to this. It's less than equal to a quantity which is known as the ergodicity coefficient of the Markov chain, where the ergodicity coefficient of the Markov chain is defined as half of the sup over S and S prime of the total variation distance conditioned on S and on S prime. Okay. This is known as the ergodicity coefficient of the Markov chain. There are various ways to compute it, approximate it, and so on. For if my chain has the property that I am converging to a stationary distribution, this is typically strictly less than 1. And normally, when you do things like Markov chain has the property that I start from two different initial states, my stationary distribution would not change. That is a consequence of this thing being strictly less than 1. Okay. If you haven't seen this before, sort of this is just a very caricature version of what ergodicity coefficient is. But for our purposes, the nice thing with this is if I have a Markov chain with ergodicity coefficient strictly less than 1, then the span norm will be contractive. If this is less than equal to 1, then the span norm will be non-expansive. Okay. Notice that this thing is always less than equal to 1 because maximum of the total variation can be 2. It's the L1 distance between measures, so maximum value can be 2. Now, what this allows us to do is the following. So what will happen is when I look at a policy pi, and I look at what happens to span of the transitions corresponding to policy pi and the value function, I will get that this is less than equal to the ergodicity coefficient of the transition matrix under that policy times V. But I want some kind of bound on what happens in this environment operator E. Okay. So, I am going to define the following. So, given an MDP now, I am going to define something which is known as the contraction coefficient of the transition P. Recall this is P1, this is the P of S prime given S and A. Okay. So, I will say the ergodicity coefficient is something which I want. This is a function of the controlled transition kernels of my Markov decision process, which has the property that this is, make sure I get the inequality in the right direction. This is greater than equal to the Pt of pi t for all pi t. So, suppose I can find a ergodicity coefficient which is greater than the ergodicity coefficient of all policies. Okay. My claim is that if I define lambda t to be equal to the sup over all S A and S prime A prime, half of the total variation distance between S A and S prime A prime, this object has this property, and in the notes I gave a proof of that. If you have sort of seen this type of ergodicity of Markov chains, it should be relatively simple to see why this implies that. If you haven't, just trust me, it is some simple algebra I can do to show that, but I have this property. Okay. Now, the point that I want to say is, suppose this is true. Okay. So, given a MDP, there is an object which is called the ergodicity coefficient. This would imply the following. If I take the environment operator and apply it to any value function, and I ask what is the span of this object. Okay. This will be equal to the span of the cost at time t plus I will write this as the operator Pt applied to V. Okay. Now, span is a semi-norm. What that means is it satisfies all the properties of norm except the fact that if the span is 0, that does not mean that the function is equal to 0. Okay. I can take a function which is constant everywhere. This is a function whose span norm is 0, but clearly this function is not 0. But other than this, span satisfies all the properties of a norm, which means it satisfies triangle inequality. So, this is going to be less than equal to span of Ct plus span of operator P applied to V, and by the definition of the contraction coefficient, this is going to be less than equal to lambda t times span of V. Okay. So, my environment operator satisfies a one-step recursion in terms of the span norm. Okay. So, only part here which is you are sort of taking on faith is that the definition of lambda t implies this. Okay. In all the properties that we will prove, our basic analysis is going to be of this form. I will show there is some property of interest. When I take that property of interest for the as what happens when I apply the environment operator on that, I get a recursion of this form, whereas there is that property of the cost function plus some coefficient times that property of the value function. Okay. Once I have this, I can get, and I need, so typically what will happen is that these action evaluation operators, I'll state that without proof right now, but span of this thing should be less than equal to span of Q. This kind of makes sense because I am just taking the same, like this is almost from the definition of span, okay? Because this will be the distance between specific actions, and span is worst case over all actions. I'll also get that the for any policy, span of this applied on policy pi t and q is going to be less than equal to span of q. So once I have the, for typically for all our analysis, what we'll get is there is a one-step property for the environment operator, and there is some form of a non-expensive property for my action evaluation operators. So this is a linear property of some sort, and this is a non-expensive property of some sort. And once I have these two properties and my dynamic programming equation, I can get bounds on the span norm of the value function. Okay? So what I can do is, okay, for ease of derivation, I am going to assume there is a lambda upper bar which is greater than equal to all of the lambda t, just so that my results are a bit cleaner. You can have this time varying lambda and do it in the algebra that I am going to show, and you will get tighter bounds, which I have shown in the notes. Okay? But the basic idea is the following: V star t plus 1 is 0, span of V star t plus 1 is 0. This is my initialization. Now, Q star t is the environment operator at capital T applied on V star t plus 1. Okay. From the one-step relationship, I get that the span of Q star t is going to be less than equal to, let's say this was constant as well, span of C, or okay, let's keep it span of Ct, I don't think it will make a difference, plus lambda times span of V star t plus 1, which is going to be equal to span of Ct. Right? C capital T, sorry about that. I'll now apply the optimality operator. V star t is t star applied on q star t, and this will imply that span of V star t is less than equal to span of q star t, which is span of Ct. Right? Let's now go forward. Q star t minus 1 is going to be E t minus 1 applied on V star t. This is going to give me span of Q star t minus 1 is less than equal to span of Ct minus 1 plus lambda times span of Vt, which will be span of Ct. Okay. Now I apply this to the value function. I'll now simply go in this space because we know how this thing works. This guy will be less than equal to the exact same quantity. Okay. I go one step further. Now I'll directly start doing my iterations on this step because sort of we know what the pattern is. I'll get span of V star t minus 2 is less than equal to span of Ct minus 2 plus lambda bar, sorry these were lambda bars, lambda bar span of Ct minus 1 plus lambda bar squared span of Ct. Okay. And continuing this way, I get a bound on the span semi-norm of the value function, which only depends on the properties of C and the properties of my transition matrix. Okay. So often these bounds are terribly loose, but it gives me some way of deriving bounds without having to compute my value function. There is a similar type of recursion here for Lipschitz constants, and we get similar type of bounds for Lipschitz constants as well. Okay. I'm sort of run out of time to do that. We'll see at the end of the next lecture, if there is time, I'll try to come back to that. But for the purpose of the next lecture, it would be sufficient to say that, so the key point here is when I get these bounds, I don't have to solve for the value function to get these bounds. Just from the properties of my cost function and the dynamics, I can get upper bounds on the span of the value function and the Lipschitz constant of the value function. Okay. So let's take a break now, and we'll meet back in half an hour to discuss what happens to model approximation. in the next 3 lectures, I am going to discuss about model approximation in MDPs, and the basic idea is we will start looking at more and more sophisticated analysis of the same problem. The purpose of this lecture is to point out what the key idea is, and once we understand the key idea, you will see that we can start adding more and more details, and we can start getting tighter and tighter bounds. Okay. So, let me start by the basic setup that I am interested in, which I am going to call model approximation. So, recall what we were saying in terms of having this continuous time MDP, discretizing it and asking how good of a discretization is. Okay. Let me take a slightly more abstract version of this problem. Suppose there is some real world application that I am interested in solving. Okay. There is something which happens in the real world. I create a model of that. Okay. My model is never going to be accurate. We do, I mean, everyone has done course in linear systems, linear differential equations, model reality. A simple circuit is not a linear system, right? There are, I put a high voltage, it's going to burn. It's only linear within some regime. Whatever model we have of the real world is an approximation. Okay. What we will be doing in analysis is we take this approximate model and we compute the, let us say, dynamic programming on this approximate model, and then we are interested in seeing how good a solution we get. Okay. There are 3 questions that I am going to focus on. The first question is, which I will call policy error. So, here the question is the following. Let me make an assumption for the purpose of this lecture, and I am going to relax this in the future, but I will make the following thing. So, from the notation of the last lecture, I have a model which is SAPCT. This is my true model, and I will say I have an approximate model. For the purpose of this lecture, I will assume that this approximate model is on the same state and action space, but may have different dynamics and cost. And again, as in last time, these are time varying sequences, not necessarily time invariant model. Okay. So, this is my true model and this is my approximate model. Now, suppose, so the first question is policy error. Yes, this is a C hat. Sorry about the writing. So, suppose I have a policy. So, there is this policy pi equals to pi 1 to pi t. My state and action spaces are the same. So, this policy is a valid policy in the hat model as well as the true model. Okay. In the real world, so this is like someone came up and said, here is a heuristic policy. I think it works very well. Here is my intuition why it works really well. Should I implement in my real system? Okay. I don't have the ability to simulate my real system. I go and look at my model, and I simulate my policy in my model. Okay. Once I do that, I solve the dynamic programming equation, and I get a value function, which is in the hat model, how well does this policy perform at every time. Okay. And I want to know, is this how the policy will actually perform in the real system? So, can I somehow bound what is the difference between the value functions in the approximate model to the value function in the real model for the same policy? Okay. So, this I will call policy error. Okay. Remember, these are functions. Okay. So, I will have to figure out what do I mean by a bound on functions. Either I will have to come up with a point-wise bound for every value of s, or I scalarize this function in some way. I take a norm of some type and I get a bound on the norm. Okay. The second question that I am going to ask is what I will call value error. I go take my approximate model, I go ahead and solve a dynamic program in that approximate model. That gives me a sequence of value functions. And I ask how good are these sequence of value functions compared to the optimal value function in the true model. Okay. This is telling me at any state what is the smallest amount of cost that I could have obtained if I start from that state, and how good is my approximate model compared to what is happening in reality. Okay. The third question is what I'll call the model approximation error, and this is the most important thing. So what will happen in this case is, I took this approximate model, I solved this model, and at the end of the day, I can't do anything with the value function, right? What I can really implement in my real system is a policy. So I get a policy from this thing, I go and implement that policy in the real world. And I'm interested in asking how good or bad is this from the best that I could have done. So how good is the performance of the optimal policy of the approximate model when used in the real model compared to the best that I could have done in the real model. Okay. This is what I eventually care about. All these other things are going to be intermediate steps for me to get a bound on this quantity. Okay. What I'm going to do in this lecture is describe all these three error bounds in terms of the soup norm. This will be the easiest to derive result, and it will be in general a terrible upper bound. Okay. We will next lecture look at the same problem and ask what happens if these were over a different state spaces. Okay. We'll see how steps needs to be modified so that I can go from same state space to different state spaces. That bound will follow the same structure and will be a loose bound, and when I'm deriving the bound, I'll point out what is the step where I get the looseness in the analysis. Okay. And finally, I'll ask what if I try to get a pointwise bound, and this will be slightly better bound, which will be non-computable because it requires properties of the true model to compute, and I'll start relaxing that till I get a computable bound. Okay. But the key thing that I want is the application that I described earlier. I have no access to the real world. Okay. All I can do is I can do any calculation I want in my approximate model, and I want to say things based on the approximations in my based on calculations in my approximate model how things will work. The bounds that I'll derive in the beginning will have the property that I'll assume I can do one-step Bellman update in the true model, and then we'll approximate that step as well. Okay. Yeah. This guy? This guy? Oh, sorry. Yeah. So V hat star is the optimal value function of the hat model. No. So this is when I use the policy pi hat star and use it in the true model. So let me take the example of, yes, right. So that's different from how pi hat star behaved in the true model. Okay. Yes. So it's not that value error is low and the model approximation error is high. The point is, I want a bound on this, right? So if I get a bound on this, that does not give me a bound on that. Okay? So this is a good indicator that okay. Here's a slight digression, but if you have you taken a course in MDPs and seen reward shaping? Okay. So I'm thinking of the simplest way to explain this. let us take the solution of a dynamic program, and suppose I add a constant to the cost at each time. My value function changes, but my optimal policy does not change. Okay. Are there other things that I can add to my cost such that my value function changes and the policy does not change? Okay. One can show that there is a whole family of functions that you can add to your cost such that the value function changes, but the cost function does not change. I can always pick a function within that class such that the optimal value function is always 0. Okay. For any problem, I can modify my cost in such a way that the optimal value function is 0. So, I can make this guy 0 whenever I want. Okay. That tells me nothing about how good an approximation I am going to have. Okay. So, I can have this to be very, very good, but my system behaves terribly. Okay. So, what I am going to focus on is the soup norm, and recall the notation that we were using from last time. So, I defined these operators, the environment operator, which is a map from the, I really cannot write calligraphic V. So, space of value functions to the space of Q functions. I had defined the action selection operator T star, which takes a Q function and gives me a value function, and the action and the policy action evaluation function, which takes a Q function and gives me a value function, right. And my dynamic program then was a composition of these things applied one after the other. First, I am going to give you some properties of these operators, and then we will come to what is the right way to look at model approximation. Okay. So, recall the environment operator this for any Q function Q, sorry, any value function V, evaluated at S and A is Ct of Sa plus summation over S prime Pt of S prime given Sa V of S prime. Okay. The first property that I have here is that this operator is non-expensive in the soup norm. Okay. What this means is, let me take two value functions V1 and V and W or V1 and okay, V1 and V2. Suppose I have two value functions. Okay. I look at the environment operator applied on V1 minus the environment operator applied at V2, and I ask what is the maximum difference between these two quantities. Okay. Now, notice, recall we were also following this, that I am going to be writing this in the short form as this plus Pt times V, right. So, what is going to happen here is both of these operators have the Ct term. So, that is going to cancel out. So, I will get that this is really equal to Pt of V1 minus Pt of V2. Okay. Now, Pt, which is this guy, is a linear operator. Okay. From so, this is really matrix multiplication. So, this guy from properties of matrix multiplication is going to be less than equal to this times V1 minus V2. Okay. Let me write it, maybe this is, it does not clearly say which norm I will be using. So, let me just write this as, if it was like this will be less than equal to summation of, I will do the same thing that we had done last time, P of S and A times soup norm of V1 minus V2. let me just use the triangle inequality rather than using the submultiplicity of matrix norms, just that it will be more transparent. Okay. I'll get this. This means I can take this soup norm out of the summation. I'm summing a probability measure. So this will be less than equal to V1 minus V2. So my dynamic environment dynamics operator is always a non-expensive operator. It does not increase the soup norm. For those of you who have sort of seen similar properties of Bellman operators, one typically shows Bellman operator is a contraction in the discounted cost setting, which if I were in the discounted cost setting, I'll get that this guy is also a contraction. If you haven't seen it, don't worry about it. We'll not talk about the discounted setting in the course. All right. Next, what about these two operators? These operators are also non-expensive. I'm first going to show T pi is non-expensive, then I'll show T star is non-expensive. So recall T pi applied at any Q function evaluated at S is summation, is simply Q of S at pi of S. Okay. Therefore, if I take T pi of Q1 minus T pi of Q2, what I'll evaluate it at S, what I'll get is Q1 of S pi of S minus Q2 of S pi of S, and this is less than equal to soup norm between Q1 and Q2. Okay. So the policy, the action evaluation function for a given policy is non-expensive. Let's now take T star and recall this was defined as T star of S equals to the minimum over the actions of Q of S and A. This is this basic proof thing which is used quite often in the type of analysis. So it's good to see how we show something for this. My claim is this guy is also going to be non-expensive. Note that in this case, so I'll start with something similar, but we'll have to do things a bit differently. So let's look at T star of Q1 minus T star of Q2 evaluated at S. Okay. What I will get is I'll have to solve an optimization problem to find what's the best action corresponding to Q1 and what's the best action corresponding to Q2. Let me assume that this guy is exactly equal to Q1 of S A1 minus Q2 of S A2. So what I'm saying is A1 is the action which achieves the minimum in this optimization, and A2 is the action which achieves the minimum in this optimization. Okay. This step is clear to everyone? Now, the property that I'll use is the fact that A1 is an optimizer. Okay. So this object is going to be less than equal to Q1 of S A2 minus Q2 of S A2. Okay. I replace the optimal action with some action. So clearly this has to be an inequality. And this guy will be less than equal to the soup norm between Q1 and Q2. Okay. This gives me one directional bound. If I flip the role of Q1 and Q2 and apply the same argument, that will give me the other bound. So I can then show that the norm of this is less than equal to Q1 and Q2. Okay. So, this is my first result, that my dynamic program can be written in terms of these three operators. All three of these operators, this is first, second, and third, all three of them are non-expensive. Okay. Questions on this? Yeah. No. Okay. So, convergence in SOUP norm will imply convergence in any other norm in finite dimensional spaces, but non-expensiveness, no. Okay. Now, the most important thing for us to derive the results is what I am going to call the mismatch operator. So, I am back to this problem that I have one true model, one approximate model, and I want to see basically how do the dynamic programs of these two models differ. And I will say the mismatch operator, which I will call D for difference, dt. This is an operator from the space of value functions to the space of Q functions. And when I take this operator on any value function V, this is defined to be equal to the environment update corresponding to the true model in V minus the environment update corresponding to the approximate model for V. Okay. Recall V is equal to C plus PT. So, this is C plus PT minus C hat plus V hat P V. Okay. So, I am taking how much. So, you see this was the key step in my DP, right. I take a value function and I get a Q function, and I am asking how much difference do I get between these two if I started with the same value function and applied different environment update operators on both of them. Okay. Now, recall the way we proved the span norm bounds in the last class. Okay. We showed what happens at one step, and we will renew that in other steps. That is exactly what I am going to do. So, for me the key result is the following. Let us say at some time I have a Vt plus 1 which belongs to V, and I have a V hat t plus 1 which also belongs to V. I have two value functions, one in the true model, one in the approximate model. I compute the Q functions Qt to be equal to the environment update of Vt plus 1 and Q hat t to be the environment update in the hat model of V hat t plus 1. This is what will happen in one step of my dynamic program. I start with some value functions which differ by something. I apply the environment update, I get two Q functions, and I want to understand what is the difference between Qt and Q hat t. Okay. I am going to derive two bounds on this, and then we will come back and write the conclusion of this theorem. Okay. This is perhaps the most important step that we are going to be doing in all the analysis. Once you understand that, everything else is going to be small variations of this basic idea, and it is a very, very simple thing. So, let me just write things down. Let us look at Qt minus Q hat t. This is equal to the environment operator applied on Vt plus 1 minus the hat environment operator applied on V hat t plus 1. I really do not have any ways to compare these, but I know what happens if I had the same operator, but different value functions, or what happens if I have different operators, but the same value function. That was my mismatch operator. Okay? So, I will massage this so that I get these two terms. So, I am going to add and subtract. I am going to say this is E t V t plus 1, and let me add E t V hat t plus 1 plus E t V hat t plus 1 minus E hat t V hat t plus 1. Okay. So, I have added and subtracted the terms in red. Yes, thanks. I will have an inequality because this is my triangle inequality. Okay. And now, I have things that I can do. This is the environment operator applied on two different things. I have shown this guy is non-expansive. So, this object is going to be less than equal to V t plus 1 minus V hat t plus 1, and this guy is the mismatch Bellman operator applied on V hat t plus 1. So, this would be okay. So, I get a one step recursion in terms of the Fuchs norm of the mismatch operator. Let us call this bound A. I will derive a different bound, and then my main statement will be the combination of these two bounds. Right? Any questions on this thing? So, it is just simple triangle inequality. Okay. All right. So, how do I get the second bound? I could have done something differently here, right? I took E and V hat, I could have taken E hat and V. Okay. So, my second inequality is at this stage I could have done E t V t plus 1 minus E hat t V t plus 1 plus E hat t V t plus 1 minus E hat t V hat t plus 1. Okay. If I do this, now this is something with the same value function and different operators. So, I will get this is less than equal to the mismatch operator applied on V t plus 1 plus this is non-expansive V t plus 1 minus V hat t plus 1. Okay. So, this thing I can come back to my result and say this had to be less than equal to minimum of the norm of dt applied to V t plus 1 or the norm of dt applied to V hat t plus 1 plus V t plus 1 minus V hat t plus 1. Okay. So, I have a way that when I go from value functions which differ by something and I apply the environment operator on both of them, the Q functions will differ by no more than something which depends on this norm of the mismatch operator plus whatever was the error in the initial time. Okay. This is going to be my basic recursion step. Okay. Yes. Yes, I'll get to that later on. So what I want to do is I want to derive certain results where I'll keep everything in terms of this. And what you're saying is there that I can refine it further by using one more inequality in terms of norms of the cost and something with the distance, and I'll come that to this in the second half of the lecture. The reason I want to keep this here for those of you who have seen, so in for the purpose of what we are deriving, I could have done that right here. But sometimes in reinforcement learning and so on, it's easier to get a bound on this because in certain situations, I can use things like Azuma's inequality and so on to give a high probability bound on this quantity directly, while using the loser triangle inequality will give me a much, much looser bound. So I'm not going to do that derivation in these lectures, but it's useful to keep it in this stage to get the final bound and only then get an upper bound from that final expression. Okay. So this result is enough for me to get the policy error bound. So what I'm going to show is the following. So this is our first main result. This is the policy error. I'm going to assume there is a fixed policy pi 1 to pi t, and I'll define quantities alpha pi t to be the sup norm of v pi t minus v hat pi t, and I'll define beta pi t to be the sup norm of q pi t minus q hat pi t. Okay. And from the fact that my policy, that the action evaluation operator was non-expensive, I immediately get that alpha pi t was less than equal to, beta pi t. Okay. This is an immediate implication that t pi was non-expensive. And I want to get a bound on this quantity. What I will get is, this is going to be less than equal to summation tau equals to t to capital T, some quantity which will depend on policy and tau, where I define delta pi t to be the thing that I had here. This is minimum of norm of the Bellman operator pi t applied on v pi t plus 1, or the mismatch operator pi t applied on v hat pi t plus 1. Okay. So I'm using small q's were just what I had defined here. In my dynamic programming, I'm always using capital Q for the solution of the dynamic program. Okay. So before I give a proof, let's just see what this means. Okay. So I'll focus more on the second part of this term. I take the I take my approximate dynamic program, I solve it, I do the policy evaluation on that, and I compute what v hat pi t's are. Okay. If I have the ability to do one step update in the true model, I can apply the environment operator for one step in the true model, I can compute this quantity for these value functions. Okay. I take their norms, and my error, approximation error, is going to be bounded by this. Okay. So this gives me a model error which only depends on the solution to the dynamic program in the approximate model and my ability to do one update in the true model. Okay. Now the proof is just one line implication of that. Okay. I'm going to give the proof in a way which is sort of is going to make the subsequent proof easier to understand. Always, 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 I'll prove these results using backward induction. Okay. Take t equal to capital T plus 1, the result is trivially true, everything is 0, that will be my basis of induction. I am going to assume this result is true till at T plus 1 and look at the problem at time T. Okay. So, at time T, I have q pi t minus q hat pi t. From the one step lemma, this is equal to delta pi t plus the norm of v pi t plus 1 minus v hat pi t plus 1. Okay? And I am done. Substitute back what my induction hypothesis is, and I get back the result. Okay? So, once I look at the problem the right way, so the trick was I broke down this dynamic program into one step where the operator is being applied, one step where I am doing action evaluation. Very simply, we can show all these operators. Just give me 1 second. Very easily, I can show all these operators are non-expensive. Triangle inequality gives me something like this, and repeatedly applying this gives me this result. Okay. Alpha is less than beta just because when I look at v pi t minus v hat pi t, note that this is equal to t pi of q t minus t pi of, or t pi t of this, t pi t of q hat t. And this is where the step becomes important, that I separated out what depends on the model with just the optimization. This guy does not depend on the model. So, it is the same operator for both cases, and we had shown that that operator was non-expensive. Therefore, this is less than equal to q t, these should have been q pi t's, q pi t minus q pi hat t. Okay. Any questions? So, what is the source of looseness in this bound? The source of looseness in this bound is this step. Okay. This is the only inequality, only real inequality that I have in the analysis. Okay. There is an inequality where I get that this thing, there is an inequality here because we were using the soup norm. I can tighten this a little bit, but not really. The only other place is that here I am using a triangle inequality, and this can be very, very loose. Okay. We will see later on how we can try to refine, to tighten this, but it is going to be very difficult to get tighter bounds on this unless I am willing to relax my the constraints that I have imposed, that I do not want to use any information from the true model. Okay. Questions? Okay. This is enough for me to describe the value error as well. Is the green pen visible to everyone in the back, or this is too light? Okay. So, I will now say let alpha star t be equal to v star t minus v hat star t, beta star t is q star t minus q hat star t. As before, because t star is non-expensive, I know alpha t is less than equal to beta t, and I'm going to show that this is less than equal to summation tau equals to T to capital T delta star T, delta star tau, where delta star T is minimum of the norm of the mismatch operator applied on V star T and the norm of the mismatch operator applied on V hat star T. Okay. Same structure of the result. This thing, I don't know why I wrote d pi here. The mismatch operators don't depend on the policy. So it's just the difference in the environment from the star functions. So again, if I focus on the second part of this bound, this tells me if I can solve the approximate dynamic program, the dynamic program of the approximate model, and I have the ability to do one-step Bellman update, I can derive bounds on the difference of value functions. Okay? Proof is exactly the same. I start with t equal to 1, the result is trivially true, that sets the basis of induction. My induction step is going to be exactly same as before. I'm going to look at q star t minus q hat star t. This is equal to the environment operator t applied on v star t plus 1 minus the environment operator hat applied on v hat star t plus 1. From the one-step lemma, I will get that this is less than equal to delta star t plus norm of v star t plus 1 minus v hat star t plus 1. Yes. Thank you. Sorry about that. Okay. So again, very simple idea. All I do is change the, it's the same thing, right? We recursively are applying something like this, and I'm keeping track of one-step errors, and I keep accumulating that, and that gives me what the error is going to be at a certain time. Okay. Now to the main thing, what do I do with model error? Rather than stating the result first, let me just give the derivation because that's simpler than this. So what I'm interested in is having a bound on v pi hat star minus v star. Okay. I'm going to use triangle inequality. I'm going to say this is less than equal to. So you see, I have a way to bound now the error if I was using this. I was using the star models of both of them. So I'm going to say, let me try to do v hat star t minus v star t. This is something that I can compute. Let me write it in a manner which is more elaborate than needed, but perhaps it will make it slightly more transparent. So you can see I have all the blue terms here. I'm adding and subtracting the red term, and then adding and subtracting the green term. Okay. the main observation now is that the red term and the green term are identical, because this guy was the optimal policy of the hat model. Okay. The first term I know how to bound, the last term I know how to bound. Okay. So, I am done. Rest of it is just moving things together. Sorry. Yeah, but I know this is going to be path cost of the future in terms of these functions. This is going to be the path cost in the future in terms of these functions. Yes. Are you saying in this triangle inequality or somewhere else? I am not going to t plus 1 at all, right? I am just adding and subtracting the red term ones and the green term ones. There is no t plus 1 here, right? And this is just the value optimal value function and the value function of the optimal policy in the approximate model. So, these two are equal. Okay. I am writing it explicitly like this because this shows that even if in some applications I cannot solve the approximate model exactly, I use some I don't know, approximate algorithm to solve a value function in the approximate model, I can keep track of bounds here. I am not going to do that here, but I can very easily add those approximation bounds here as well. Okay. So, now in terms of writing the result, it is only that obviously the upper bound is going to be with this and this. I just want to keep track of the right value functions. Okay. So, I will not write that in terms of these delta pi's. What I am going to do is the following. I am going to make the observation that what I am interested here is this policy error of v pi hat star. So, I am going to take the second term here for v pi hat star. The second term for v pi hat star is equal to v hat star. And in this guy also, I am going to take this term, which is v hat star. Okay. So, if I take that instead of min, I just take this upper bound here. In both these cases, I am going to get terms which is the mismatch operator applied on v hat star. So, my final result becomes this is less than equal to twice summation tau equals to t to capital T, the norm of the mismatch operator applied to v hat star t plus 1. Okay. So, if I have the ability to solve the approximate model, if I have the ability to solve the approximate model and compute the value functions, I have the ability to do one step mismatch operator of the value functions, which requires me to do some calculations in the true model. I can tell you what the model approximation error is going to be. Okay. Now, here this, as I said, this bound is loose. The looseness here is coming from this triangle inequality. Okay. And this guy is really, really loose. Okay. What is happening here is, imagine a situation of the form where the hat model was the true model minus some constant cost. Okay. When I go to these things, I will get that twice of that constant as my error, while there is really no error in the approximation. So, forcing this triangle inequality here makes my bounds loose, but the advantage is this is a very, very simple derivation, right? We did not do anything. It is just two triangle inequalities that gives me the result. Questions? Okay. Going much faster than planned. So, let me give also one result. So, I had mentioned this thing about if I was doing some sort of sampling based algorithms to compute things, I may want to to bound these types of quantities using Azuma Hofstadter and so on. If I'm interested in that, and that happens in reinforcement learning when people are using sample complexity bounds for generative models, this is not a good quantity to bound. Okay? So what will happen? So in certain instances, it is nicer to get a bound in terms of V star t rather than V hat star t. Okay? That's not useful if I'm interested in the setting that I explained in the beginning, but if I were trying to get some probabilistic inequality to bound, the thing would be typically if my hat model is a sampled model from the environment, it would be a random variable. This guy becomes a random variable, and it is difficult to get bounds in terms of differences of random variables, but you can get bounds if this was a constant and I was getting the mismatch operator in terms of the V star. So there is some value in some settings to get a bound which is looks at d of V star t rather than V hat star t plus 1. Okay. So let me go back and look here. So I can't really, so for this object, I could have used V star t also. For the first guy, which is the value error, I have one term which is V hat star. For the other guy, I do not. I have V pi hat star t plus 1, and I have V hat pi hat star t plus 1. I don't have V star. So I'm going to spend some effort trying to upper bound this in terms of V star t and get a bound which is going to be much, much looser than this, but has the advantage that in certain analysis, if we want sample bounds in terms of Azuma Hofstadter, we can use that upper bound. Okay. So what we are going to do is, I am going to state a claim that, let me call this quantity alpha t. Okay. I am going to claim that alpha t is less than equal to alpha t plus 1 plus twice summation tau equals to t to capital T mismatch operator at tau applied to V star at tau plus 1. Okay. I'll prove this claim in a bit. Let's just believe this claim is true. If I take this claim and I unroll it, okay, I recursively start substituting what is the value of alpha t plus 1 in terms of alpha t plus 2 and so on. What I will get is that alpha t, so by unrolling, I get alpha t is less than equal to twice summation tau equals to t to capital T tau minus t plus 1 norm of d tau V hat star tau plus 1. So what happens is I get a linearly degraded bound. This is the how far I am from time t, and I'll have the error at that thing which keeps on accumulating over time. Okay. For those of you who are familiar with bounds in reinforcement learning, these are the type of bounds where we get one additional horizon factor in the error analysis, and this bound is much, much looser than the bound that I have here, which is in terms of not having that additional factor of the horizon. But the advantage of this, which is useful in some cases, is that I get a result in terms of V star tau t plus 1. Okay. So let's see how we will prove this result. And I must admit, to me, this is always I mean, the result is simple. It's just using triangle inequality. I have no intuition on whoever first come up with this triangle inequality, and you'll see why I am saying that. Yeah. So let me start with the proof of the claim. What I want to show is that the norm of V pi hat star t minus V star t, I want to bound this by something. So I am going to do is what I did here. I am going to break this down into this triangle inequality. So I'll get the term which is V hat star t minus V star t plus V pi hat star t minus V hat pi hat star t. Okay. This object I know is upper bounded by the norm of the this is upper bounded by this summation t equals tau equals to t till capital T, norm of the mismatch operator at tau applied to V star tau plus 1, right. This is what I was saying earlier, that for the value error I can get a bound of this type. This is the term that I have to figure out. Okay. So I'll focus on this term. This term now is V pi hat star t minus V hat pi hat star t. I know from the non-expensive property and the fact that they are using the same policy that this is going to be equal to less than the environment operator applied on V pi hat star t plus 1 minus the environment operator in the hat model applied at V hat, I'll write it as star t plus 1. Okay. So I've done two things here. This is the same action evaluation operator. So that is non-expensive, so I can get rid of that operator here. And this guy is the optimal value function in the hat model. So I'm just, rather than writing at V hat pi hat star t, I'm writing at V star. Okay. But I used the fact that this was the optimal policy when I got rid of the action evaluation operator. Okay. And now is the bizarre triangle inequality, which is I'm going to add and subtract terms till I get terms that I can work with. So what I'm going to do is, this is less than equal to psi t V pi hat star t plus 1 minus, and I definitely need colored pens here. So I'll add one thing which I know how to evaluate, which is the environment operator applied on V star t plus 1 plus I now take the environment operator applied at V star t plus 1 and I am going to take the hat thing applied on V star t plus 1 and I am going to take the hat thing applied on V star t plus 1 minus the term which was remaining, which is E hat t V hat star t plus 1. Okay. So, by doing this thing, I have come up with series of terms, all of which I know how to bound. Okay. First one is the same dynamics operator, but different value functions. So, this is non-expensive. This is going to be upper bounded by V pi hat star t plus 1 minus V star t plus 1. Okay. The second guy is the same value function, but different dynamics operator. So, this is going to be upper bounded by the mismatch operator at t applied to V star t plus 1. And the last term is the same operator applied to different value functions. So, this is going to be equal to V star t plus 1 minus V hat star t plus 1. Okay. Rest of that is simply this guy I had already bounded above. I substitute that back in. That gives the factor of 2 here, and this guy is alpha t plus 1, and I am getting this term. This was at t plus 1, so this plus this gives me twice of this. Okay. So, there is this somewhat bizarre triangle inequality, but I am really trying to massage terms so that I get everything in terms of things that I can bound. And I get a recursion on this error, which is of this type, which gives me this additional linear dependence. This is never a useful bound if I am just interested in doing model approximation, because I do not have access to V star at all, plus this is a looser bound than the other one. But if I wanted to use results from concentration inequalities and so on, it's easier to use in this version of the bound than in that version of the bound. Okay. Questions? All right. So, now we look at this is a good bound, provided I have the ability to do a one-step update in the true model in order to compute this mismatch operators. What happens if I do not have that ability? Okay. So, I am going to make the following assumption. I am going to say, suppose I know something about the accuracy of my model. Okay. So, I have some way of describing how bad my approximate model is. And the simplest way to describe that is I will give you a definition of model distance. I will say, given an epsilon, which is a vector of some epsilons, all positive or maybe greater than equal to 0, sequence of deltas, I will say model m hat is an epsilon delta approximation of model M if the following is true. 1, the soup norm difference between Ct and C hat t is less than equal to epsilon t. And second, I am going to sort of in this thing go back to IPMs. I'll assume I am given some function class f, and I am going to be defining my IPMs with respect to that function class. I'll say that if I look at the IPM distance between the transition dynamics for a given SA in the true model versus the transition dynamics for a given SA in the approximate model, this will be a function of S and A, and I supremize this over all SA. So, worst case IPM distance between any two rows of my transition matrix, and assume that this is less than equal to delta t. If these two relationships are true, I say model M hat is an epsilon delta approximation of model M. Okay. So, the way to think about this is I am thinking of a ball of radius epsilon t around C, and I know my approximate model's cost is within that ball. I am thinking of a ball of radius delta t in terms of the IPM distance around the true model, and I know my approximate model is within that ball. Okay. If that is true, I'll say I am within a radius of epsilon and delta of the true model. Okay. This is the IPM distance with respect to a function class f. So, what the way we have defined this is equal to supremization over all functions in that function class of so, in particular, if I take this as the function class of functions whose half of their span norm is less than 1, this gives me total variation. If I take something which is Lipschitz constant less than 1, this gives me Wasserstein, and in general I can have other types of functions as well. And the key property that we had for this is that if we look at any function not necessarily in the function class, the difference of expected values, this is going to be less than equal to the Minkowski functional of this function times the distance between mu and nu, and this would be half span of the function for total variation, Lipschitz constant for the Wasserstein distance. Yes. Not necessarily. Okay. For instance, span is not a norm. Right? It is half span in case of total variation. That is not a norm. Lipschitz constant is also not a norm. Like, so it doesn't need to be a norm, but there is some notion of some kind of a semi-norm, and so as I said, right, the way to think of this is I get a ball around origin. This is the family of functions that I have, and this is how much do I need to scale back the function to bring it back to that ball. But that distance does not need to be a metric. Okay, so if not a metric, it doesn't have to be a norm also. Yes, so the case in which, so one of the common cases in which sort of we have had a lot of success in numerically using these algorithms is if you look at the function class where calligraphic f is the space of, is a Hilbert space which is a RKHF, recursive kernel, I don't, anyone remember the full thing? Reproducing kernel, yeah, sorry, reproducing kernel Hilbert space. And in that case, this is really a ball of norm 1 in that RKHF, and this would be the norm in that space. But If I'm in a general space which does not have the reproducing property, I don't think we can, like you can still define all these things. The question comes, is this a metric on probability spaces? And I'm not completely sure on the top of my head if the metric property will work, if sort of that requires some extra conditions, right? So in general, anything defined like this, if I remember correctly, is a semi-metric. It is the metric property which requires some difficulty. So some of these bounds may be applicable in more general settings also, but one has to be a bit careful if we are using some properties in the analysis. Okay. So if I have this, then I'm going to make the following claim, which will now give me a way to connect model approximation to the approximation results that we obtained last time, that if I look at now the mismatch operator applied on any function v, this is upper bounded by epsilon t plus delta t into the Minkowski functional of the value function. Okay. I'll give a proof in a second, but let's try to understand the implication of this. So now if I suppose this was total variation, right? So L1 distance between my transition matrices. And I know that is less than delta, the cost only differed by epsilon. We had derived these results where the right-hand sides were in terms of the mismatch operators applied to v hat star of t plus 1. Okay? And I can upper bound that with epsilon and delta times the span of v star t plus 1. Okay? So that means if I'm interested in model error, and I know that my approximate model is within epsilon delta distance in total variation of the true model, I can get an upper bound that the difference of using the approximate policy in the true model is going to be less than equal to twice sum of these epsilons plus sum of these deltas times the span of the value function at different times. If I had solved the value functions for the hat model, I know exactly what the span of this thing is. Okay? So I get a computable upper bound without knowing anything about the true model, except that it is within some epsilon delta radius of my, without anything about the true model, except that it's in epsilon delta radius of the approximate model. Okay? So this gives me a very, very nice way to get bounds. I'm going to sort of write that down. So recall the result that we had was v pi hat star t minus v star t is less than equal to twice summation tau equals to t up to capital T, the mismatch operator at tau applied to v hat star at tau plus 1. Right? This would mean that using the previous result, I can upper bound this as twice summation tau equals to t to capital T epsilon tau plus delta tau rho f of v hat star tau plus 1. Okay. Now, let me give the derivation of this, and I'll come back to this result to elaborate on this a little bit more. Okay? But before sort of we start talking about the proof, any questions about the implication of the result? Yeah. So what you can do is, if I have two different data sets, so what happens is, suppose, how do I know a hat model, right? So one way of knowing the hat model is I observe the system, I gave you 100 inputs for every possible state action pair. I observe what the next state is. I use the empirical counts as an approximation for this. I can use basic concentration inequality results to say how quickly is this concentrating to this guy. Right? So you have different results on concentration of samples from an IID, how quickly does empirical distribution converge to the true distribution in total variation. There are similar types of bounds in how quickly does an empirical distribution converge to the true distribution in Wasserstein. I can use those bounds to get high probability bounds on delta. I don't need to know the true probability distribution. The rate of convergence does not depend on the true probability distribution. Okay? So, yes, I'll have to make some assumptions, right? So, what I'm saying is, for my purpose, go to a probability theorist, ask, this is the class of distributions I have, tell me how quickly does the empirical distribution converge to that. Okay? If they have studied that problem and know the answer, I'll use it. If they don't know the answer, I'm not going to spend time trying to derive an answer on my own. Okay? So I'm just reusing existing results to say, you have to do this, right? If you don't know how to do this, this is not going to work. But for a lot of problems, I do know how quickly do empirical distributions converge to true distributions, subject to modeling assumptions, right? I need to make some assumptions about the true distribution. In the finite state, finite action cases, I really need no assumptions. Okay? In continuous spaces, I'll never get concentration in total variation. I'll get concentration in Wasserstein, and that depends on the dimension of the space I'm in. There are other ways to relax some of these results. Other questions? Okay. So let's look at the proof. And this is really just going to be triangle inequality. So my proof is going to be, recall that dt of v is really Et of v minus E hat t of v, which is equal to Ct plus Pt of v minus C hat t minus P hat t of v, which is less than equal to Ct minus C hat t plus Ptv minus P hat t v. Okay? And kind of I am done. This is my epsilon t, this object for a given value of S and A. So if I look at Pt of v minus P hat t of v evaluated at a particular S and A, this using the IPM inequality, this is going to be upper bounded by the Minkowski functional of v times the IPM distance between P, T, S and A and P hat T, S and A, and then I just take the sup norm of this. Okay. So again, this is a very, very simple observation that IPM distances give me bounds on the norm of the mismatch operator. All my errors are in terms of the norms of the mismatch operator. Therefore, I can get upper bounds in terms of the model error and property of my value function. If I'm computing model error in terms of total variation, this is the span norm. If I'm computing model error in terms of Wasserstein distance, this is the Lipschitz constant. If I use RKHS, this is what is the error is in terms of what is known as MMDs, maximum mean discrepancy, and this will become the Hilbert space norm of my value function. So this is useful if you're doing some linear function approximation and so on to compute your value function. Okay? So I can have this very, very straightforward thing to get a family of bounds depending on how I want to do approximations. Okay? I want to talk about one last thing before concluding, and that goes back to the question we asked at the beginning of the previous class. That is, if we were doing, if we had a model on a continuous space and I was doing discretization, can I tell how many discretizations I need? Okay? I'm not completely there because that model is defined on two different spaces. Next lecture we'll see how to study cases which are in two different cases. But the point is, this result, what this would mean is, I pick a number of discretization cells, I compute the value function in those number of discretization cells, and I say if that's sufficient or not. If not, I discretize further and I resolve the problem, right? So I have to iteratively resolve the problem to get whether I am within the right accuracy or not. And it may be worthwhile to just say, can you give me the number of cells that I need so that it will be sufficient, okay? Without having to keep on resolving this guy. So in that cases, it's useful to get an upper bound on this quantity without having to compute solve the dynamic program, right? And that brings us to what we did in the last lecture, right? So if I'm doing total variation, so I'm going to call these things instance independent bounds. And the reason I'm calling them instant independent is currently my assumption is there is a true model. I take an approximate model which is within the epsilon delta radius, and my bound depends on which model I picked within that radius. I want to now give a bound which does not depend on which model was in that radius, so I don't want it to depend on the specific properties of this model. Okay? And for that, what I can do is, so what we showed last time, right, that span of V star t is upper bounded by something like, I didn't write down the final expression, but it was something like lambda bar t minus tau plus 1 times span of c tau, right? I might be off by the coefficient of 1 here, just check the note for the exact expression, but we had this uniform upper bound on the ergodificity coefficient of my Markov chain, which gives me this type of relationship. In the worst case, there is no contraction, so this guy is equal to 1, and I'll get this is equal to span of the value functions upper, the span of the value, the span of the cost functions at each time, and all that I need to do now is do this calculation in the hat model. So I know what is the span of the cost function in the hat model, and by this I can get a instance independent bound for which I do not have to solve the dynamic program in the hat model to give a bound on the model error. The catch is that this is going to be a very, very crude upper bound, right? So we'll get I'm losing information, so my bounds have to be looser and looser, but this is useful in certain instances. Similarly, I did not write that down last time, but sort of in the notes we have a derivation for a Lipschitz constant of the result, which is in terms of, I'll just write some function of the Lipschitz constant of the dynamics and the Lipschitz constant of the cost function. The derivation for this is very, very similar to what we did for the span norm, and in cases I need that, I can substitute this function there, again with the catch that this upper bound is going to be a fairly crude upper bound. Okay? So this concludes everything that I wanted to talk about for these models. In the notes, I also show how I can use these results to get, for instance, in an inventory control problem, if we ask the question, what happens if I estimated my distribution incorrectly? So at some distribution, I sampled it, and I estimated from samples, and it was somewhat off. I can get upper bounds on the Lipschitz constant of the value functions and use that to figure out how bad my approximation is in terms of errors and distributions. And you can do the same type of things in other problems. Okay? What we are going to do next is see how all of this works when I don't have the same state spaces in both cases. And then, as I said, the key looseness here is the triangle inequality that we are using in deriving our model error bound, and we'll come up with sample path based bounds which do not have this limitation, but require me to be able to do more things in my true model, and we'll figure out ways to approximate that. All right. So let's stop here.